Kandala. Please just call me Kandala. I'm Professor of Biostatistics at the Department of Epidemiology and Biostatistics at the University of Western Ontario in Canada. Also, I'm affiliated with the School of Public Health at the University of Witwatersrand in South Africa. So it's a pleasure for me to be with you today for the module on regression analysis in public health. So we are going, I hope you received the course outline, and what we are going to do this morning or this afternoon is just to go through the basics to make sure that we all are at the same thinking, at the same level. I know that perhaps some of you have gone through all the material I'll be sharing with you this today, but for me, from my side, is really to make sure that we moved at the same level, and especially also the audience is varied, meaning that there are people from different background. So, and please, as we move along, feel free to ask any question. We can ask questions as we move along. So I don't think that we should wait till the end of the class to try and ask questions. And it's important that as we start, the concepts are very well clarified and also well understood, so that there is no confusion at the end. But I hope maybe most of you have heard about the regression analysis and have done a regression analysis. And please, if you are familiar with it, maybe focus on what you have not done before. So the analysis of continuous data, so, and the concept of simple and multiple regression model. So the learning outcome today, I hope that by the end of the session, you should be able to fit a simple or multiple linear regression model. You should be able to interpret the result, and you should be able to check underlying assumption for linear regression model. And this is the later part is very, very important, in the sense that anyone can take the software and fit a regression analysis and have results. But the most important is now, as a specialist, data science specialist, you should be able to comment on the fitted model to see whether the model is a good model and why you believe that the model is a good one, and whether you are able to comment on the underlying assumption. So by definition, linear model, and I'm going through just an overview. I think perhaps you, most, as I said at the very beginning, you are familiar with this. So by definition, a linear model, or we start with a simple linear model, regression, is a statistical method that really summarizes the relationship between two quantitative variables. So linear regression need really at least two metric variable. This can be ratio or interval scale variable. And in terms of mostly people ask the question, what is the sample size that you need to be able to quantify the relationship between two continuous variables in terms of regression? So the rule of thumb is at least 20 observations. So the variable we are predicting is called the dependent variable, and it is referred in the regression languages as y, and the variable we are basing our prediction is called the independent variable, or the predictor, or the covariate, and is referred as x. So when there is one predictor, then the method is called simple regression analysis. So simple meaning that one predictor or one independent variable. And then obviously when you don't have, you have only, you have at least two, then it would be multiple regression analysis. So I think most of you are very familiar with the coefficient, the correlation coefficient, which actually indicate that two variables are associated with one another. So the regression analysis is an extension of the correlation analysis. When you correlate two variables, so there you will have, usually we will give you the that the two variables are associated, they are related, but you will not know what is that exactly about the kind of the relationship of that correlation. So with that, an extension, because the correlation coefficient is a limitation, so that this is extended to regression model to help and investigate, especially when you have two or more variables or more relationship between variables that depend. So the regression analysis help to find the average relationship that you may not really be able to see by eyes. So on your data, an example of this is, for example, if you want to find the association or the relationship between unemployment and government spending. So this may not be obvious. So, and then you are able to use a regression analysis to try and quantify this relationship between unemployment and government spending. So in this case, for our example of government spending and unemployment, so the linear relationship between the explanatory variable, in this case, and the dependent variable is, this case also is very, very obvious, unemployment and government spending. So we need to determine which variable is our explanatory variable and which one is the dependent variable. So I will come into more detail about this later. So why is the value of the dependent variable? In our case, is spending. And you may have this in any context. So it's just an example. And we can also try to contextualize this example in the area of public health. So this may be health spending in any given country. So Y is the variable, the dependent variable. So the health spending, and then the X is the independent variable, that is unemployment. So usually the regression analysis is characterized as yi equal to alpha plus beta and multiplied by x, which is the independent variable, and plus the error term. So I'll comment about this later. So the I there is the observation, because if you are talking about government spending on health, so you may have this weekly or monthly or yearly. So the I there to represent the unit of analysis. And this can be if it is weekly, so week 1, week 2, if it is monthly, month 1, month 2, and so on. So the two equation there for the linear regression model, so it has two components, the Y. So the dependent variable has two components coded in color. So we have the red, which is the random part, and the first one in green, which is the non-random component. So for our example of an unemployment year, so we need really to estimate the alphas and beta, which are, we said they are not random, they are non-random, so it's part of this non-random part of the model. And here we have the constant, which is usually the average of Y when the X are equal to 0. So the beta are called regression coefficient or the slope, and usually measure the steepness of the regression line. And I will come later about explaining that. So the random component is called the error term of the observation. If you are measuring government spending on health, depending on the unit of analysis, depending also on the observation, you may be making some error. So that is the error part. So the technique of the regression analysis really estimates the alpha and betas using the observed value of X and Y. In the case of government spending on health and unemployment, so if this is our example, if it is done weekly or monthly, so you may observe some health spending monthly and then try to estimate the alphas and betas using the technique called ordinary least square regression. And when estimating this monthly or weekly, if you want to repeat the to check in a year's time or in a 5 years time whether there is a relationship between government spending on health and unemployment, So this model may help you in fact, just measure the X value. This is unemployment, and be able from those values to predict the government spending. So that is really the big difference between, or the importance of regression analysis, of simple regression analysis as compared to the correlation coefficient we are familiar with. So with the regression, simple regression, we are able to know also the direction of the relationship, but more importantly, also be able to predict. So to predict the Y when we observe the X. So the main idea about the simple linear regression is that you will usually place the best fit straight line into the point, and so that this relationship can be generalized later. And it also shows how much the variation of the independent variable explained by the independent variable. And more importantly, we make the assumption when we are doing a simple linear regression analysis, we are making the assumption that the relationship between the dependent variable and the independent variable is linear. So one example or health example of this may be, when fitting, I did mention that when fitting regression, linear regression, you are really trying to find a best fit of the line. So you can see here, the Y, our Y is here. This may be any health outcome. And in our case here, maybe government spending on health. And the Y here is the independent variable, which is unemployment. So in this case, you are able to see, with the value of X, which you observe, you can measure, and you can measure it in different way, maybe in a questionnaire or any other way. And then when you have them, you want to repeat the process after, then you can predict also the Y with this equation. So, and in this case, you can observe that we have here the Y increases by 1 unit, 1, 2, 3, 4, 5. This is important to know, but the value you are predicting increases by unit of 10. So 10 units. And this is what we indicated earlier on, that the betas, the steepness, so this is the speed in which the Y increases. And the alpha here is the intercept. So the value of Y, the average value of Y when X is equal to 0. So, and in this case, the unit is here 20. So I hope that so far there is no question. So I don't know with the other module, okay. So I wanted to go back. So here it is clear that the value, the added value, first of all, we need with the regression, we need a straight line. A straight line. And while we have this straight line, we are able to see or to define what is the intercept. So the intercept clearly is the value of y when x is equal to 0. So in this equation here, if x is equal to 0, then 0 multiplied by m is equal to 0 plus c. So we have the constant, which is the value here, the average value when x is equal to 0. So that is one thing. And the other thing is that we are able, with the observed value of x, we are able to predict the y. And this is also the added value of the regression technique. And we also know the speed in which the slope are increasing. So that is the m here. So in this case, it's by 10 units. So, and with this, so given our equation there, we should be able to predict if x is equal to, the average value is equal to 5.3, we are able to compute the value of y, to predict the value of y. So, and in this case, you can always compute this even manually. So the idea with the regression, linear regression, is to find the line of best fit. So one other example in terms of health is to find the relationship between the body mass index and hip circumstances. So you can see here that we have data using real data from type 2 diabetes and using 227 observations. So you can see that these are all the one dot there is an observation of a patient with type 2 diabetes, and they measure their BMI and hip. Then you can draw this, and the idea with linear regression is to find a straight line between the y and x. As you can see now, you can draw this from here. And when you do this, finding the best fit, you are in the business of regression analysis. So in practice, the point we observe will not fit exactly on a line. So we only estimate the best fitting line. So as we can see in the previous, there are some points that are far from the line we draw here. But remember, it's to do with generalization and to do with the summary. So we may not have, in the best case scenario, you will want all the points to be on that line. But in practice, that is not the case. And the line that we are going to fit is, as I said, is a summary to generalize. So it's a total absolute distance between each of the points and the fitted between the small and the biggest. So the total distance really make up of the residuals that is not accounted by the fitted line. So, and that is the model. So you are in the... So please mute your microphone when you are talking, when you are not talking. So with the best fit or the line, so we use really this to predict future value of y if we have new value of x. So, and as indicated in the example of government spending, if you are measuring government spending, unemployment, weekly or monthly or yearly for 2003. So, and you can predict the government health spending for this year. Next year, you may not be able, or you may not be able in the position because of the money to carry out, to go and measure at the same time government spending, health spending, and unemployment, but you'll be able simple next year to measure government, the unemployment. So you can use the model that you've fitted last year to predict the government health spending. In the same vein, so for our example of IP and BMI, we are only allowed perhaps to measure a patient IP. Then we can use the equation there to estimate the diagnosis of BMI. So pretty very useful in terms of technique to allow us to also, is cost effective as compared to the correlation coefficient where we need to outcome be measured at the same time and find the association. But for the simple regression analysis, this is not the case. So with this, so we can observe BMI and observe also the IP and have this relation, this straight line, and have the relation and predict with the value of the IP, and then predict our diagnosis of BMI in the future. So now that you are able to know what is the business of simple regression, a linear regression, I mentioned at the very beginning that it's important that we know whether the model we are having here, the linear regression, is a good model, and there are assumptions that underline the fitting of a linear regression model. So now we will go through those assumptions, and these assumptions for linear regression model usually can only be tested after the model has been fitted, not before. So you have collected your data, you have collected your government health spending and data on unemployment, or you have collected your diagnosis of diagnosed BMI and also IP information on your patient with type 2 diabetes. So, and you fit a linear regression to find out the relation and relationship between independent variable and dependent variable. So, and you want to have that equation to predict future value. So then you have to check assumption whether your model really fulfill the requirement of fitting the model. So one of the assumptions, the first one is linearity. So there is the assumption that your dependent variable and independent variable need to be linear. And the second one is the normality of residual, the error. So you have to see that the error of measuring your diagnosed BMI or measuring your government health spending are normally distributed. And then I'll get later to what we mean by normally distributed. So, and then there is the third one is the constant variances. So that is homogeneity of variances of residual, and sometimes it's called homoscedasticity. So these are the three assumptions that need to be fulfilled when you are fitting a linear regression and when you want to decide whether these assumptions are fulfilled and your model has the best fit, basically. In terms of the first one, linearity, so the relationship, as I mentioned before, between the independent and the dependent variable need to be linear. So this, you can test this in different ways, but the simple ways is just to make a scatter plot of residual versus the independent variable. So you have your independent variable in the x-axis and the residual of them in the y-axis. And in terms of the normality assumption, so the dependent variable must be normally distributed, and usually the curve to check this, there are various ways. You can draw a histogram to check whether this assumption has been fulfilled for your data, or you can also use the QQ, what is called normal QQ quantile plot, the QQ plot. And then for the constant variances, so the error along the regression must be equal. That's meaning that they are constant. So when you plot the individual error against the predicted value, the variance of the error will be really constant. That meaning being equal. And to check this, you can also use the scatter plot of the residual versus the fitted predicted value. And this can be only done, as I said at the very beginning, when you have fitted the model. After fitting the model, then you can check these assumptions. Okay, so far there is no question. No, I have to go back. So In terms of graphic, I mentioned Wiki plot, I mentioned scatter plot, and so on. So we need really to have the three underlying assumption. The key underlying assumption for the linear model represent them in terms of graphics, linearity, normality of residual, and constants of variances. So in terms of constants of variance, so we have here the graph usually, and I indicated that you need really to represent this in a form of scatter plot. So you have the error that need to be constant, that is equal. And what do we mean by equal? So for example, you can see the arrow here, the line, the red line. So all are in here, these are in the x-axis, we have the predicted value, and here we have the error, the individual error. If you measure government spending, so here in the y-axis, you will get the individual weekly or monthly health spending error that you make. And here you have the predicted value. And the constants of the variance, meaning you can have this arrow to mean that they are stable. If we are at 0, yeah, there is a line, and the distance between 0 to 200 is equal to the one from 0 to minus 200. So you can see the consistency there, and with it, you are able to say whether your variance are constant. So the assumption of residual being normal meaning that this must follow a normal distribution, the Gauss distribution, which is a bell shape with a mean of 0 and equal variance. So the second one is that a linear relation between dependent variable. So in our case here, health, government spending, or diagnosis of BMI, and independent variable is the IP, or the unemployment. So there should be any systematic pattern between the residual and the dependent variable. So, and that you are able to determine whether the relationship is linear. And in terms of the constants of the variance, we have just seen the graph. So we need to have same variability above 0 and below 0. So there is stability, there is no obvious demarcation or variation or between the two positions. And more importantly, each pair of observations are independent from each other. So that is, if you are measuring BMI and in one person to the second one, so their BMI must be independent, or the government spending from week 1 to week 2, they need to be independent from each other, so that we are also equally sure that the residual are independent from each other. The error we are making for measuring the BMI in person 1 is independent to what we are measuring BMI in person 2, and so on. that means the assumption of independence. So in terms of the normality of residual, the model residual we saw there, epsilon, it is normally, we say that it's normally distributed, and this at each level of the independent variable. So we can see here that this is the Gauss bell shape. So we can see that it's linear and it's normally distributed, the error. And in terms of the assumption of linearity, we also indicated that this, suppose, can be checked through the graph, a scatter plot, or any other graph you are familiar with. And we should observe that the relationship between X, the independent variable, and Y is linear. So in this case, the graph here, so obviously this is linear, and this one here, if you observe in this way, you are able to determine that the relationship is not linear. In this case, it's quadratic. The constant variances. So we saw one way of determining this, and we use the residuals and drill the arrow, the red, to see whether the variance is constant. And this is also another way of checking this. The variance of the dependent variable is constant for different level of independent variables. So we can see here, and in this case is equal variance across all the range of the predictor. And at here, there is unequal variances. So we can see, but still falling in the linear line. So sometimes you hear about unequal variance. That means that the distance you are seeing there is not that equal. So it's unequal. Whereas in the left-hand side graph, we have equal variance of the outcome across the range of the predictor. Okay. So now, as a data scientist, you should be able to comment when you are being approached. You should be able to comment whether the model you are fitting has violated the assumption of linear regression model, and whether the model you want to predict is not a good one. So sometimes those assumptions are violated, and when you notice that, you should be in a position to say that maybe the prediction you are making may not be a good one. So that is in practice. If you have measured the IP and you do not want IP and BMI in your patient in a sample, and you have an equation that you need to predict for the next sample. So, and you check the assumption, and if some of the assumptions are violated, so you should be as an expert in data science, advise that perhaps that model may not be a good one to predict the value of the diagnosed BMI for the next wave of patient. And to see that, so violation of the assumption, as you can see in this graph, if these assumptions are violated, most of the time, you as an expert also need to bring solution. So instead of working with the observed value, you may log transform the data to improve the situation. So if you are working with government spending or unemployment, so you may need to log transform this so that you have a perfect or a nearly perfect linearity between the independent variable and the dependent variable. So in the first place, you can see obviously that the assumption is violated. So there are tools for checking this assumption. So any software that you use, maybe SPSS, Stata, R, and any other statistical software have tools on how to check these assumptions, to check whether the distribution of residual is normal. So that is with a mean of 0, the average of 0, and a constant variance. So you can draw an histogram of the residual. So the histogram of the residual will help you check the normality assumption. And to test whether the linear relationship assumption is fulfilled, you can also draw a scatter plot of the dependent variable against the independent variable. So this should really look approximately linear, or you may also plot the residuals against the independent variable. So this should be also randomly scattered. Then to check the constant variance, so you may plot the residuals against the fitted predicted values. And if a random scatter of points appear, then the assumption is met. And if the scatter residual progressively increase or decreases, then the assumption is not satisfied. So, and a visual inspection of this with line, the red we saw there, can really quickly make you identify whether the assumption has been fulfilled or not. So you can see that this is clearly an indication of what is required for fitting a linear regression, and especially in this case, a simple linear regression. Not only the fact that you are able to fit it, but especially being able to try and make a judgment in terms of the model, the fitted model. Why? Because the model will allow you to predict, and the model is the best fit of the data. You must have a line, the best fit, in order for you to generalize. And before you make any prediction, you are able to make sure that the model you are having is a good one that will help you or characterize your sample and may help you predict future value. So checking of assumption is very, very crucial in the regression analysis business. But most of the time when we see people fit the regression, fit their models, they are not concerned with the assumption. They did not check the assumption. They did not even mention them in the reporting, whether the model is a good one. So usually what we do is, as most of us today in this session, we have cars and we drive the car every year, every day, and we just assume that the car are running, they're good. We don't even have the time to check whether there is there's something, the oil and so on, or something maybe be wrong. And we just go to the seat and start the car and drive and reach from point A to point B and say that, okay, this is fine. As you can see, the danger of that. That is usually what we do when we report or we do the business of regression in our report, in our papers. And we don't really, we assume that this is a taking, and there is no need of reporting whether the car is, we have checked whether the engine oil is fine or this and that. So the car, we assume that is fine. But as you can imagine, this is not most of the time. The car may be faulty and may not get you from point A to point B. So now as a specialist, data science specialist, you will be able to also, as you report your regression analysis, you should have just a line or a sentence to say that I did check the assumption, I did check that the model fit is good, and you may report that you may not be able to show all these assumptions, but you may also try to, just in a sentence, to make sure that you report to your readers that you care for the model is a good one, and you did check the assumption. But this is sometimes requested by, if you want to publish your work, requested by reviewers, and you can always have them in the appendix or have them somewhere, and to say that, to report all these assumptions. So before we proceed to the actual how to do this in SPSS or in Stata or in R, so I want to entertain a question, and I need also maybe a comfort break. Sometimes it's very difficult in the online, if somebody wants to go to the toilet or something. So I just request a 5-minute comfort break, so that we'll return to, what is the time? Yes, in 5 minutes, if this is okay. Kelvin.
Okay, Prof.
Yeah. Is that fine? Is that okay?
It's okay, Prof.
Yeah, okay. So please prepare some questions. For those who are familiar, prepare also some good questions. For those who are not familiar with the business of regression, also ask some naive questions so that we can all clarify and move on. Thank you. So I think I've seen some good question in the chat there. The first question is that whether is it possible to talk about linear regression when the independent variable is qualitative? That is the first good question. And the second question was that what did I mean by y variable? Okay, perhaps I need to quote it as, can we still talk about linear regression when x is qualitative? This one question. What is meant by, the second question, what is meant by independent and dependent variable linear? So, let's start with the first one. What is meant by independent and dependent variable linear? So there I indicated at the very beginning that we need, in a regression analysis, we need one variable that is called dependent variable, and another one is called independent variable. Dependent variable is the value that depend on, we are able to predict from another variable. And independent variable is a value that we are predicting from. So one example of this I indicated is the government health spending. So we can predict government health spending from the level of unemployment in the country. If the government is not spending that much, we will have a lot of unemployment. So, and then we can predict, if we have in the X independent variable, we have high level of unemployment. So we can guess whether the government is spending a lot of money or not on health. And this also, we should refer the independent variable to the unemployment in the health sector. So you can see that the unemployment, the health spending depend, there is a relationship between the two. So, and whether this is linear meaning that this may go, we can put a line, a straight line between the two, and whether they are going up or going down, this line may be going to the negative or going to the positive, depending on the situation you are in. So key there is the fact that we have an independent variable that, as the word suggests, is depend on others, can be predicted from others, and we have the independent variable, which is the variable in which we are predicting from. So that is, I hope that is clear. And the linearity is to do with the relationship between the two. So the line can be put in a straight way, and this can be negative or can be positive. So that is the response to the first question. The second question is to do with the fact that if we have qualitative variable independent variable, can we still talk about linear regression when the dependent variable is quantitative? Because at the very beginning, perhaps I mentioned the fact that you have a situation where the two variable y and x, the independent variable and independent variable are linear, are quantitative, are ratio or scale. So yes, you can still have a linear regression analysis when one variable is qualitative. So what determines whether the model can be linear is usually not the independent variable, but the dependent variable. So you determine which kind of model you are going to fit from the dependent variable. If the dependent variable is a quantitative variable, then regardless of what you are going to have in the independent variable, you should be able to fit the linear regression, because the dependent variable is quantitative. It can be a scale or a ratio. In this case, you may replace unemployment if you want to check the relationship between government spending, and in the independent variable, you can see whether this is in the independent variable can be the health sector, whether it's private or whether it is public. So if you have the qualitative measure in the independent variable, health sector, private sector, or government hospital or public sector, so that is a qualitative, and you want to check the health spending, so it's linear, you are able also to fit this and predict in the sector of public or private. So I hope that is clarify the question. So I have another question here. You mainly talk about plot to check assumption. What about some formula tests like lack of fit test? Yeah, there is a Broch-Pagan test, Shapiro. Yeah, so yes, I mentioned that there are various ways of checking assumption, which is correct. You may use graphics, you may use test or statistical test. So, and usually, so for normality, there are various ways. You can have statistics to check the Shapiro test and so on. You can have them to test, but as always, so it's good to be practical and to go for the simplest way of doing this, because I believe that with the test, you have to interpret statistics, which is not usually nice for everybody, especially in the health sector. So visual inspection with graph is, I believe, very simple and very straightforward to check. So, and what I'm advocating here is not that I'm advocating just one way of checking this that I'm doing. I'm saying that there are several ways of checking, But for me, I prefer the graph, which you can inspect with visual inspection and determine this easily. So you may use other way of checking this assumption. So this should be clear.
Okay, Doc. Sorry.
Yeah, go on.
Oh, okay, thank you. I think I get the point now. I was a bit confused. I think when you do exploratory data analysis, especially for data science, this is where the testing, the checking that you have actually discussed, you can actually use it there. Now, for me, it makes a bit more sense because you are then checking for some of these parameters through visualization in exploratory data analysis. I think that's where it applies in as much as we can do other tests, but for that purpose, these actually are very important.
Yeah, thank you. But I will also extend that to not only exploratory data analysis, but also very, very important when dealing with we mentioned that is at the very end when you fit your regression analysis. After you fit this, you are in a position to explore these assumptions. And the better you explain this, the simpler you are able to explain this or to show this, the better. So, and that is what also I wanted you to understand, that yes, it's exploratory, but also this can be final for your model, and I will advocate this way of doing if you are aiming a wider audience.
Okay.
Instead of coming with the Shapiro test and discussing the p-values and so on.
Okay.
And this is also for public health journal. It would be better to explain this in a graphical way than to go for the statistics.
Thank you so much for that one.
Okay. Okay. So now, if there is no further question, so we should be able, really, we understand what is a simple regression analysis. We mean there's no confusion between, ideally, you have two quantitative variable, independent variable, quantitative, and dependent variable quantitative. You are able to see a straight line and look for the best fit of those lines so that you can generalize, you can summarize this in an equation in order for you to predict the values in a further experiment or a further sample. And in order for you to predict this in a further sample or further experiment, you should make sure that the model you are dealing with is the correct one. And this is by checking assumption. And we have indicated three sets of assumptions: linearity, constant of variance, and there is also normally distributed. And we then discuss how in practice this can be done. So, and I indicated that there are several ways of doing this, but the most simplest and clearest one, I believe, is going through the graph, because we can just inspect this graph and comment as a judgment there as a data scientist to try and see whether this is okay. And sometimes when the visual inspection is not clear, then you can turn on to the statistics so that you can see. And this is a bit also sometimes complicated, because if you may have a p-value that the borderline. So yes, with that, that will make you to make a, because there is the p-value, as you know, is a clinical significance, is not statistical significance. So if you have a p-value, you may be quick to judge that assumption. But when you have an inspection, a visual inspection, there may be also disagreement between experts. So, and you may have a different view, but in general, as we have indicated that this should not happen because we are looking about summaries. We are not looking about perfect situation. In practical, we should have compromise to see that, okay, we agree that this is a summary, we agree that this is a tendency, although there may be some deviation, but we should come to a conclusion that this is a generalization, this is a summary of the situation, and we can represent this in a picture. And I hope that is clear. So I'm not a fan of SPSS, and especially in, sorry, is there somebody want to talk?
Yes, please. I raised my hand earlier, but I think you didn't.
Okay, I can't see. Please, I'm focused on the slide. If I can't see, please stop me and also ask a question. Yes, please go ahead.
So it's on the regression. Sometimes when you run the regression, you realize there are some missing values. And I may want to know what may account for that, and if there is any way to treat such missing values after running. Let's say the data set will be full, but then when you run, let's say either adjusted and then even the crude odds ratios, at the end of the day, you don't find any values for such data. I don't know what, if you have an idea what may account for that and how to treat them.
Okay. Yeah, thank you. Sure. So yes, sure. So this example, yeah, your question is about when you measure health spending, government health spending, and unemployment. So in, can you hear, is that Ghana or Nigeria? No, I'm just joking. You're from Ghana or Nigeria?
Ghana.
Ghana, yes. So you now have some missing information about counties in a specific region for any reason. So you have a proportion of counties. If this health spending, government health spending is measured at the county level, and you have specific values that are missing in, this may be in a specific, because the level of measurement is county. We should agree, is county. So each a region may have, in Ghana, can you give me an example of how many counties they have in region in Ghana?
We have 16. 16,
okay. So assuming that within one region, you have maybe one specific region, so there are 5 or 6 counties that do not report this government spending. So in another province, so you may have also some counties that are missing. So, and remember, we are talking about averages so that we can, in next year, be able just to see the employment level and predict the government spending. But if you have, for example, in 16, you have maybe 5, 6 that are not reporting the government spending, then you may run into your model at the end may not be a good one. So, and this is the question that our colleague is asking. How do you proceed about this? So there is obviously missing values. And missing value, unfortunately, is a completely different area that needs good attention. But since you mentioned the question, we just try to explain, but it's a different, entirely different area in analysis of data, because there are several ways that you can deal with these missing values. And the important thing is to acknowledge that missing value is an issue. If you have 10 counties that does not have the health spending, and your prediction may not be valid when you predict, and you have to do something about this. So one way of dealing with the missing, first of all, you have to see whether the pattern of the missing. So assuming that you are measuring health spending in the province, one province that have 16 counties, and you see the 10 counties. So first of all, you have to quantify the percentage of the missingness. Is it with 16, is it just one county missing? Or is it 1%? Is it 20%? Is it, what is the percentage of missingness? When you establish that, the second thing, so if it is just the missingness is 1%, you may ignore that. 2% you may ignore depending on your context. But if in this case, we believe that missingness is serious because there are 10 counties that are not reporting, so I cannot go ahead and predict. So the second thing, you will try to see what is the pattern of this missingness. Is it random? So you have 16 counties. Are they, if you are measuring government spending weekly or monthly, is it the same county in week 1 or in month 1, month 2, month 3, and so on? Is it the same county that are having these missing values? So if the pattern of missingness is at random, so missing, you can find it in week 1 or month 1 in county 1 or in county 16, and in the next month you can find it in county 12, county. So this is random. You will see that this is random, but if you notice that it's the same counties that are reporting missingness, this is not random. The pattern is not random. So you need to know that. And why you need to know that? Because there are statistical regression model that when you do the regression model, if your missingness is at random, you will still get a robust estimate. You can still average, because the pattern of missingness is not the same. So it's at random, and the estimate of your health spending you will get there will not be affected by the missingness. But if it is not missing at random, then there are statistical technique that you need to do. And this is called imputation. You have to impute your data. Imputation means that, for example, for health spending at the county level in Ghana, so you measure health spending in county 1, county 2, and 16. You measure it weekly. You measure it monthly, depending on your unit of analysis. If the health spending for month 1 or month 10 is missing, you can take the average value. For example, if in month 10 is missing, you can take the simplest way is to take the average value between month 9 and month 11. And then because it's missing, you can assume that this may be the average of the two. And then you plug into your missing estimate. This is the crude way that you can deal with missingness. But there are so many techniques in statistics. And in fact, it's an expertise by itself in an area of research that deal with missingness. If you are interested, please, you can explore or send an email and I can point you to the literature in this area. But mostly in practice, it's like you go and do your health survey. You go and you are dealing, depending on what you want to find about a person, and you go there, survey, ask something about that person, but you go and then the person is not there in the household. And you can impute the value by maybe taking the response for another person, a friend, a close friend of that person. And that can be also called imputation. There are several techniques. So in short, so that is how you deal with missingness. And missing is actually a problem, and you need to address this. You need to quantify this, and you need to address this before you move on to fitting the baseline and fitting, predicting with a good model. I hope that clarifies your question.
Okay, Doc. I sent you a message some few minutes ago. I don't know if you have received it. And if that is okay, then I can do that after checking on the question I sent.
Okay, I asked the question under discussion. I wanted to share with a data to help with the question asked. Is that the question?
Yes, please.
I don't understand the question. Can you clarify that, please?
Yeah, so yeah, with respect to the question that I asked and the explanation that you were given, yeah, I wanted to send you just a one-page document to support the question that, or what I sought to clarify earlier by asking the question that sometimes when you run the regression analysis, you find some, not all the values will appear for the adjusted or the crude odds ratio, and what might or what may account for that. And if you have to treat the data in such a way that if you have to treat the data such that you don't have such an instance of missing some of the values for the adjusted or the crude odds ratios in your regression analysis.
Yes, Adam. So what I've explained is that because, yeah, when you run a regression analysis, for example, there are data or unemployment in the county that are missing, then you carry on to run a regression analysis. At the end, you may not have the regression value, or if it is a logistic regression, you may not have the odds ratio and so on. So, and this is because of the amount of missingness will not allow you to have a correct estimate. And what I'm saying is that in that case, you need to do imputation at the very initial stage of your analysis and data analysis. You need to impute the value to go through those variables and see, establish whether missingness is at random or missingness is not at random, and then impute the value. And imputing in this case is meaning replacing the average value, which is the simplest way for government spending for those missing value before even you run your regression analysis. Then you go back and impute or do sophisticated technique for running imputation, and then you impute the data, have the correct, replace those values, and then come and run your regression analysis to find what kind of odds ratio is given you. So I hope that is clear.
Yes, please. Thank you very much.
Okay. So for those, I said for those familiar with SPSS, so there are steps here on how you can check whether your model is the best fit or not. So if you have your data, how to perform regression analysis diagnostics. So for example, you have BMI, again, IPS. So there are steps here, very easy to follow. If you have a SPSS software, so you just go to the menu, as SPSS is a menu-based software. Yes, I was just saying that we need to check the model in any software. As a data scientist now, we'll be able to see whether the model we are fitting is a good one. So, and there are the slides here. Okay, you can see that there's a straightforward step that need to be taken. So for those who are familiar with the SPSS, so it's a menu-driven software. So you go to analyze regression, and then there is linear regression. You put your dependent variable, in our case is BMI, and you also enter your independent variable, which is the IP. And then while going to the statistics, you will see linear regression statistic dialog, and you follow those steps to get to the checking the assumption. So they are here, and hope to share this perhaps with you, and those with SPSS can familiarize themselves with checking those assumptions. But if you have any question, please feel free. So in Stata, for those also using Stata, so there are also, you can check this with a graph. So how to check that the residual are normally distributed. So you can use the histogram and also overlay the normal Gauss normal distribution. And you can, as our friend also earlier mentioned, you can use the statistic, the Shapiro and so on, to see whether, and judge this from the p-values, whether it is normally distributed. So this year I'm focusing only on graph, not necessary, because you can check this normally normality assumption with graph, but I believe that is very simple and straightforward and can be explained to any reviewer from any background, that the model is a good one and the normal assumption was fulfilled, and this is how I check the normal assumption. As you can see here, the mean is 0 with the constant variance, and this is clear to explain. And also checking the linearity assumption. So for the case of BMI and IP, so you can see that this is obvious from this, that most of the points here are concentrated on this line, regardless the fact that there are some deviation, but the compromise here is to make that with this concentration of points on the straight line here, make this assumption fulfilled, that we can safely assume that the diagnosed BMI and the IP are linearly related. And also here we can see the scattering of residual and IP in terms of the variation. So although there are some outliers everywhere here, but we can make this compromise to say that the variation, there is no major variation between the residual and the IPs. So this is to do with the constant, how to check that the constant variance assumption. And in the other plot I showed there, you can make some line from here to, from negative to positive. So basing on 0 here, and see the distance between 0 to here, and the distance between 0 to minus here. Although there are some deviation here, but most of the points are concentrated in this area. So we can see that we can safely say that the variance are constant. So checking assumption also in Stata, for those familiar with Stata. There any question? Somebody trying to speak there? Okay, so for those who are familiar with Stata, to check the linearity assumption between the independent variable and dependent variable. So this can be best tested by the scatter plot of residual versus the independent variable. Here, all the points approximately follow the straight line. So although we have some departure from here, but as I mentioned at the very beginning, regression business is to do with summaries. The estimation is to do with summaries, with generalization. So we can safely assume here that most of the points concentrate on a straight line and ignore those that are far apart. And in practice, you may not have a situation where you have a perfect relationship. That is also very true in real life. You may not have a perfect marriage relationship or a perfect friend. sometimes you have to make some compromise and average your relationship with your partner. You say that they are mistake, but we can make this assumption, or we can summarize that most importantly, that your relationship or the action of your partner or your friend has been positive. So the relationship can be considered normal. So the same thing in statistics here, you make those compromise. And also for the checking the normality of residuals assumption. So to check this, so you can have a instator. So this is a histogram. You overlay a normal plot, so you can see now that is your residuals are normally distributed. And you can also do the QQ plot, which is here, the quantile plot. This is called the quantile plot, the QQ plot, or this is the kernel density plot. So you can overload this with the normal plot to see whether normality of residuals is fulfilled. The assumption of normality of residual is fulfilled. Although here you can see at the very beginning, these are points that depart from the straight line. This one here and this one here, but we can safely assume that most of the points lie on a 45 angle and lie on this straight line. So we can safely say that the residual are normally distributed. So the histogram here shows the distribution of residuals. You can see now here is Q to a tail on the left hand side, due perhaps to relatively few large observations. So here, perhaps there may be, but in general, you can see that the assumption of normality can hold in this case, because it is normally the graph you have just overlaid with the Gauss graph is that fits perfectly. Okay, I have a question here that Rodrigue is asking, why do we ignore outliers and when to ignore outliers? Yeah, these are good questions. So we need to respond to them before we proceed. So yeah, please, I've said that why do we ignore outliers? And when to ignore outliers? Why? We ignore outliers in this context when we are looking at the residuals. I did not mention that we ignore outliers in our research. No, that is not what I said. But when checking the assumption, and we are dealing with residuals, then we can ignore them because they depart from the linearity line. As we can see that the summary of points are on the line, the linear line, but it's just some few ones that depart from the linear. But in practice, in real life, if there are outliers, you need to deal with them. You need to deal with them, and there are techniques in how to deal with it. This is the same, equally important for the missing, as we said. So if they are missing, you need to quantify them, you need to deal with them, because any regression you will do, or any good model you will fit, will depend on those data. And you need to deal with them at the onset. And this is equally true for the outliers. Assuming for the government health spending in Ghana, so you may have outliers and you are dealing with counties. You may have outliers of health spending of county within Accra, where there are rich, very rich, where the government is sitting, and there they have the latest equipment or the latest, they spend a lot of money there. So in this, if you are collecting maybe a figure on health spending in Ghana, you may have excessive health spending in some county in the district or in the region of Accra, because they are rich and because there is the government mostly where the county where the government is situated. So as always is the case in Africa, health spending is not homogeneous. Depending on where the government or the minister is from, it may favor some county or some region. President is from, they may favor. So these may be outliers, and you need to deal with them. There are also techniques of how to deal with the outliers. This one is to ignore those districts, to make an analysis with the richest county in Accra. So remove them and have scenarios that what will the model will look without these richest outliers. And then compare this when you put the richest county there. Sometimes this may skew the all regression coefficient. So that is very important that you make this sensitivity analysis with scenarios to know whether your outlier is skewing your estimate, your regression estimate, so that you can have a scenario where you present the data with outliers and without outliers, so that you see the impact of the outliers. So the bottom line that you have to deal with outliers as you have done for the missing values. But in terms of model assumption, if you have the residuals, so, and if you proceed with your analysis without dealing with the outliers, then that is in the situation where I indicated that you can, because you are dealing with the residuals, you can ignore the outliers and pretend that the relationship is normal. And that is where I also gave an example, real life example of your relationship with the partner. Sometimes your partner can deviate very, very, very much. The relationship can affect your relationship with your partner. But since you are called to live with the partner for years, so you need to make compromises. You need to average those actions and see that most of the time your partner has not, the action have not deviated from what you have been living during this time that warrant cessation of the relationship or impact the relationship. So, and you need to make those compromises to say that, to summarize or to generalize, to say that most of the time your relationship can be deemed to be normal. And that is ignoring some deviation. And this may be extreme one in your relationship. But in this case, or assessing, generally speaking, your relationship with your partner, you can say that most of the time, the action are normal, can be deemed, your relationship can be deemed normal. You will not come to mention those instances where your partner have some action that really could have impacted your relationship. So I hope that is clear.
Yes, thank you, Prof.
Yeah. So checking also the linear assumption in terms of variance, I think we mentioned this before, the constant variance. So variation need to be constant. And this is to do with usually the residuals. So you can see here, and this is embedded in theta, very simple, very straightforward. So you can see this is 0, positive, negative residuals. And although there are some outliers there, here and there, but you can see that these residuals, the variation here is constant. So it's at the same level. So then you can safely conclude that the variance are constant. And this can be done using a scatter plot of the residual versus the fitted model. So we discussed before how this can be done using SPSS. Here also are some steps how to run a linear, for those who are not familiar with Stata and SPSS, who have not done this before. So there's also a step here how to run a linear regression model using both SPSS and Stata. So I don't know who are using Stata, who are using SPSS. So I just wanted to run over and just as an overview, go quickly. And perhaps most of you here are very familiar, are already expert in this, but just in case. So you will have a drop-down menu in SPSS and then go to analyze, regression, linear, be able to do all this, click on the statistics, and also see whether your coefficient is going, the estimate are going to have confidence interval. And also there is the box for model fit, which is important that you check your model, and then you can have this So at the end, you can have the graph that we have discussed. And in this model box fit also there are statistics that can be, if you are interested in graph, you tick the graph. If you are interested in statistics, you can also tick the statistics. So in this case, you will have real data on IP and on BMI as indicated here. So you can see there are some missing values. You need to deal with them in the IP. There may be also some outliers. You need to deal with them. Past that stage, you can go to fitting the regression, analyze regression linear as indicated there. So first step, analyze regression linear, and then you need to choose, you will have this box, you will need to choose the dependent variable and independent variable. In this context, we are having a simple regression. So the second step, you choose the dependent and independent variable, and you go to the statistics there, the fourth step. Then you have to check also the model fit, estimate, also have some confidence interval. So you can choose whether it's the 95 confidence interval and so on. And then continue. After that, you can validate your model and have your model output. So this should be very clear to anyone that is familiar with the SPSS software. And you will have the models fit there in terms of ANOVA with the F statistics, with the p-values, and so on. So I can see there are so many comments on the chat. I don't know whether to have a look at them, see whether there is. Okay, no, this is not to do with question. Okay, we are fine. So, and then, sorry, you will have the statistics that you need to have there to check the amount of variation for the R square, and so on. So perhaps if people have trouble on how to, with this step here, what is the coefficient of variation, for example, the 36.9%, and so on, please ask some question. And I'm assuming here that you are familiar with this concept of coefficient of variation and so on. So, and your model significance, the model fit here, you can see the p-value where to judge, which is less than 0.05. So then the model may be a good fit, but you need to confirm this with the diagnostic test to check whether all the assumptions we just mentioned are fulfilled or not. So we will have the value for intercept and the value for the slope. So the constant here and the value for the slope there. So And we indicated at the very beginning that the simple regression model is the business where we try to estimate the alphas and beta, that is the constant, the intercept, and the slope using the least square method, ordinary least square method. So we estimate this with the model here as being the value, the constant is equal to minus 13.44, and the slope is 0.40. So this is our final model, and we can really be able to first write the model for further prediction, and also determine whether the model is a good fit, and also try to interpret these results. What does this mean? So these are our regression analysis for our BMI and IP. So we can see that this, the average, the constant, has been estimated by the model to be minus 13.441. And the slope has been estimated at 0.40. So we can now have, if in the future we want to predict our BMI in this population of type 2 diabetes patient, we can only measure the IP and be able to predict this with the model we are having here. The equation we are having there. So this was with SPSS. The same procedure, we can do this with Stata. We can also do this with Stata. So the command, as you know, Stata is a command-driven software. So running a BMI, running a simple regression model in Stata, you have just to put regress, put the dependent variable, in this case is blood pressure difference, and the independent variable is the age, assuming that you are investigating the relationship between the blood pressure difference and age. So here also you will have these values or these tables. Here the output, the Stata output, where you will have the R square, which is the amount of variance that is explained by the, in this case, is the BP difference when estimating the regression line or the age. So in another word, the BP, 17% of the variation we see in the BP difference can be explained by the age of the individual. So this is the explanation for the R squared here. And the model statistic here indicate that there is a linear relationship between the blood pressure difference and age. And it is statistically significant because it's less than 0.05. as you can see here. So the model we have here is a good fit, judging for the p-value. So there is a linear relationship between blood pressure difference and the age of the individuals. And there is this, so that the blood pressure difference can be predicted from the age of the individuals. But this prediction, the variation there is only 17%. That, sorry, this variation can explain. So the p-value is there. As indicated there, this is for age. After you have access for the model in general, the model fit, you can also move to the coefficient, the age, the independent variable of your regression analysis. So you can see here, this is age, and the dependent variable, dependent variable is the blood pressure difference. So the value there of the p-value is less than 0.05. So, and we should be able to interpret also this result. So this means that a unit increase. So the coefficient here was 0.073. What did this mean? This means that an increase by 1 unit of the age, it increases the blood pressure difference by 0.73. So, and you know, for example, age is measured, whether the age is measured, whether it was measured in month or measured in year. This also make a difference. So the unit there of age, depending on the unit in which you are measuring age, this may be a year. So 1 year increase for the patient will result on an increase of 0.73 of the difference in blood pressure. And this is, judging for the p-value, this is statistically significant. And also there is an interval, confidence interval there. So this can go as the variation of this difference can be as low as 0.66 and as high as 0.83. So with this, we are satisfied with the model equation. We can write this down. Blood pressure difference is equal and minus 11.82, which is the constant. This is the average difference when the age is equal to 0. So this is plus the slope times the age. So now with this model, and when we are satisfied it's a good model, then we can make some prediction. So assuming that a patient is 70 years old or 30 years old, is in our next sample, we will only know the age of our patient. So, and we can predict the blood pressure difference. So with our equation. So if the patient is 70 years old, then we can predict the blood pressure difference. So plugging the age here, you will have the predicted value of 39 millimeter of mercury for this different blood pressure difference of a patient that is 70 years old. And for a patient that is 30 years old, so you will have a difference of 10 millimeter of mercury. So this should be really clear here. If there is any question, so I can always clarify on the prediction. Okay, before we proceed to the multiple versus simple regression analysis, I think rather we have some question about the simple regression analysis so that we can proceed to the multiple linear regression. And if there is no question, perhaps we need also a break, as we have been going on for the past maybe 1 hour and a half or 2 hours, I don't know. So is there any question? If not, then we can have maybe a break. Kelvin,
I have a question.
yes, please, go
Can
ahead.
you please go back to the previous slide? I just wanted to ask, like, based on the p-value, I understand that it's a good fit, but then R squared only explains 17%. What about the other 80% that is not explained? Because it just seems like the R squared is too small, which then it just feels like it's not a good model, like based on that, because there's still a larger variation that hasn't been accounted for just based on this R squared.
Okay, yeah, you are right, and you are right in the sense that you may have some doubt about the validity of the model, but this usually depends on the situation in which you are in. So I will explain. So you are right that the R square in our case here indicate that only 17% of the variation we are seeing in the BP can be explained by age. So there is an amount of almost 80% that is we cannot see from the age. So we need really to collect some other information to try and increase this variation here so that we can see what exactly explain the BP difference that we see in individuals. Is it age plus gender? Is it age plus province of residence? Is it age plus genetics or what? So now, usually in the business of simple regression analysis, as you remember, we have only one variable, one independent variable, and that qualifies the situation to be simple regression analysis. So in practice, it would be naive for somebody to say that what the difference we see in BP blood pressure can be only explained by age. So, but remember, we have bivariate two variables. So this, at this point, perhaps should give us an indication to just say that, okay, remember your notion of correlation. So there is relationship between age and blood pressure difference. The relationship is there, is linear, and we can see it from this p-value. So there is a relationship. So which should really establish this, that there is a relationship. But the variation here may not be able to give us any useful information. For here, you can say that, okay, what you can just say is that the fact that there is 80% of the variation that cannot be explained by age, then we need it. We need this, and this simple regression analysis may not be informative. We cannot conclude from this. So that is the only message that this may indicate. And that's why we need to see the other side, how to increase this 17%, to look for the remaining 80%. And this can only be done by looking beyond the age of the individual. And this is done by multiple regression analysis that we are going to explore further. Did that answer?
I was just going to say yes, that makes sense. Thank you so much.
Okay. Any other question, please? So if Kelvin, is it okay for us to go for a break? I don't know how this, you have been running this in the previous session, whether you have also a lunch break or when to get this, or is it instructor specific? You
Yes.
go what you get. Is Kelvin around?
Prof, I'm here. I said it's instructor specific. So you decide when or how.
It appears that Kelvin is not around.
He's speaking, I think, but we cannot hear him very well.
Okay, Kelvin, we cannot hear you. Are you there?
Yes, I'm here. Please, can you hear me?
Yeah, please. Can you? We wanted to maybe have a break. We had a good break. So we were at the point of trying to see what is going on with multiple regression analysis, the concept. So we already went through the concept of single regression analysis. We indicated when this technique is used and why is it used, especially in terms of prediction, to differentiate it from correlation. And also, we needed to test the hypothesis, to test the assumption of the model, whether this is a good model to proceed for prediction. And in our last example, we also saw that when looking at the difference between blood pressure and age, the model, although is a good one, but age can only explain 17% of the variation we see in blood pressure difference. And one colleague mentioned that really this is not ultimate because we are missing almost more than 80% of the variation. And then I indicated that, yes, this is correct, and we need to find out what else can explain the difference in the blood pressure difference apart from age. And this is why we need to introduce the concept of multiple regression analysis. So in a simple regression analysis, we have only one variable, age. Then in multiple, as the word says, we are going to have multiple independent variables. So instead of having only age, we need to find out which other variable may have or may improve on our dependent variable, on what we observe in the difference in blood pressure. So by adding those variables, so this maybe is, the multiple start by 2. By adding this variable, then we have the concept of multiple regression analysis. And remember, this is something that we need to do because we believe that one variable, one independent variable may not be the whole stories that explain what we see in the dependent variable. We cannot predict the difference in blood pressure simply by looking at age. We need other things that go along with age. This may be gender of the person, maybe also the genetic of the person, maybe something to do with the environment, and so on. And that's why we need to extend this notion of simple regression analysis to multiple linear regression model. So with our model that we had only X1, we can now add X2, X3, and so on. So, and this is where this is, we can try to investigate some more variable that can influence our dependent variable. So, and also at the very beginning, you will remember I mentioned that you define which type of regression analysis by the dependent variable, because there was question that if we have a qualitative variable in the explanatory or as independent variable, can we still call it linear regression? I say yes, if the dependent variable is continuous, if it is quantitative, regardless of the fact that we are having a qualitative or quantitative independent variable, we are going to run the linear regression model. So the contrast to the continuous outcome or the continuous dependent variable is binary, and for that, the model becomes logistic regression because you have a binary outcome. This may be life or alive, a life of death. So binary, a qualitative outcome. So back to the multiple regression linear model. So all the assumption we saw there for model fit, for good model fit, still all for the multiple linear regression analysis. We should be able also to, when fitting our multiple linear regression, we should be able to check the model fit, and in the same way that we check them for the single regression, linear regression model. So this should be clear by now. The difference between simple and multiple is the fact that we are adding more variable to our independent variable. And this variable can be sometimes confound the effect of what we are seeing in the independent variable. For example, if we are looking at the blood pressure difference, we know that it is associated with age, but age alone cannot predict this difference. This difference may be confounded by other factors. The fact that the patient is a male or a female. And so those variables that interfere with the relationship between blood pressure difference and age are called confounding variable. And that is why in the regression, the multiple regression analysis, you are able to add some more variable. This may not be key variable, but they confound the relationship that you have between the independent variable and the dependent variable. So in our case, for the example of blood pressure difference, we were looking at age as an independent variable. In Stata, it is very simple to add in variable. So the blood pressure difference with age may be altered or confounded by the BMI of the person, the body mass index of the person. So you just add the body mass index of the person. You also, this may be confounded by the fact that the person is a male, the patient is a male or a female. So you also add the qualitative variable, that is gender, defined as male or female. And you may also add other variable, is the diabetes status of that patient, whether the person is diabetic or not. And these are all factors that may alter the relationship we have observed between age and the blood pressure difference. Now going back to our simple regression analysis with the output, we still can see that the test statistic here is highly significant, meaning that we are still having a good model with a p-value that is less than 0.05, 0.05. The model, but we will be also interested in looking at the R-square, the variation. So from 17%, we saw that age can only explain 17% of what we see in the blood pressure difference. Now, there has been an increase of R, so we have the R is now increased to 34. So we can see that the variable we have added have increased our precision of what we know about the difference in blood pressure. Not only age, but if we are to include the gender, the BMI of the person, or the diabetes status of the person, we are almost having double of, that can explain double of the variation. So 34% of the variation we see in the difference in blood pressure, but that is still not the norm. This may not be all we need. So you may increase this exercise by adding other variable. And this, you can do it by looking at the literature, because when we do research, we do look at what was done previously, or what the causal mechanism of blood pressure entail. So for that, you can look at the literature, how to determine what are the other variables that you need to include in your multiple regression model. Or you may test this by using a bivariate analysis, looking at the p-value, looking at one variable at a time, one variable at a time, the association between difference in blood pressure and gender, whether that was significant. And then at the end, you may decide what variable to include in your multiple regression analysis based perhaps on the p-value of the association in the binary or in the bivariate analysis, or you may look at what the conceptual framework indicate. In your conceptual framework, you may have some indication of what may be the mechanism in which difference in blood pressure can be associated with patient. So after the model, after checking the R square, after checking the p-value of the model, so you will also need to look at the individual variable. So you can also see that the p-value of the effect of age, adjusting for gender, has improved, and also adjusting for BMI and diabetes is less than 0.05. So this meaning that this model has account for the variability due to sex, the gender, BMI, and diabetes in terms of the variation we see in the blood pressure difference. And again, you need to interpret the result here, the coefficient, the betas, and also the constant has changed dramatically. And also for here, we still have the same interpretation as we did for the simple regression analysis, a unit increase in age. If age increased by 1 year, this is associated, if age was measured in year, 1 unit increase in age will be associated with a 0.75 increase in the mean blood pressure difference. And also you can look at the statistic there. So it is highly statistically significant at the 5% level. And this difference can go as low as 0.66, as higher as 0.75. 83. So nothing has changed there. So similar statement can be made for the other variable, having adjusted for the other variable. So for example, for gender, you can see whether gender adjusting or differentiating between gender, whether that make the difference. And the p-value here is not statistically significant, meaning that maybe gender, regardless of gender, what we see in the difference in blood pressure is not affected by the gender of the patient. So, and these kind of interpretation can be made with other variables, the diabetes status, and so on. But key there is the fact that R square has increased, the model is still is good, and we are able to account for other factors that may interfere between the relationship between age and the difference in blood pressure. So the F, remember the F statistics indicate the linear regression model of a good fit because it's less than 0.05. And this already we have explained all this. And although it's 34.4% of the variation, that you will wish to have more of the variable. But in some situation, this may not be the case. Maybe this is what you can be closer to get in explaining your outcome. But in some situation, you may have more. So the interpretation of the result in terms of the beta coefficient, because we have the regression analysis and the betas and the alphas, we indicated that the alphas is the constant and the betas is the slope. And this is very important when you report in terms of journal. They are standard of reporting. So sometimes people put the F statistics, sometimes people put all information that are not really required. But in terms of reporting in scientific journal or in conferences and so on, there is some good practices that you need to adhere to. And that is, so for example, here, and depending also on your audience. So you may report, look at the audience, you may report on the p-value. And sometimes if your audience is not specialist, they may not be able to know what is the p-value is. And perhaps the closest to them will be the confidence interval. Or you may make a compromise, putting both, because confidence interval and p-value, they are almost saying the same thing. They are trying to convey the same message. So it's to do with the significance of our estimate. And then you will make your own judgment as an expert, data science expert, that you are dealing with it kind of health professional, and perhaps the confidence interval will be better to understand that your estimate of 0.40, you can include the 95% confidence interval, that this varies as low as 0.36 and as high as 0.44. And it is statistically significant, judging by the confidence interval or judging by the p-value. And the constant there is minus 13.44, and also covering the confidence interval, which is statistically significant. So, you can then predict, you may predict the diagnosis of BMI just using the IP, and a new patient that you have in your clinic that have a hip of 120 centimeter. Using this equation, you can predict the patient body mass index using the formula there. So, and this is very important in terms of the reporting in journal, article, and so on. So you are not required to report all the tests that you have done there, or you are not required, you are required just to present in the sake of clarity, in the sake of to be concise. You are obliged to adhere to this way of reporting, very simple and straightforward. So we have now some other, this is just an question and answer scenario. We have still in the health sector, dependent variable is the peak expiratory flow rate, which is measured in liter in a minute. So you have a constant of this value, and you have also the age that the interview, this age will measure in years. So you have this value here, and you have also the p-value there, so confidence interval and p-value. So now the question is, the beta coefficient for age interview show that every year increase. So whether if you see you are reviewing as a data scientist expert, they have sent you the paper with this result. So in the reporting, the authors write that the beta coefficient for the age at the interview show that for every year increase in age at the interview, there is an average increase of 0.014 in this peak expiratory flow rate, with 95% confidence interval ranging from minus 0.019 to minus 0.008. Is this statement true or false? From what you have seen in terms of reporting. is this statement in this way of writing, is it true or is it not true? I need an answer, please.
So I think it's false
I think it's false.
Okay.
because of the minor sign.
Because of
It's a decrease.
why is it not? Why is
It's
it false?
It's a decrease actually.
So there is, okay, that is, yes, I agree with you, but there is also something else that I need you to notice. So there is, we can see there is a decrease. They are talking about average increase, which is completely wrong. So we should be talking about decrease. What else? Is anybody able to see this? What makes this statement false? Is the disruption in voice resolved, or is it still continuing? Is somebody having difficulties in the voice? So I think this is to do with okay, I want really you to tell me what else. Before even proceeding, you are now reviewing this paper, and this paper needs to be published. But as a reviewer, you are now an expert, a data scientist expert. You should be able to detect what is wrong with this statement in terms of reporting. The first detection is that the person, as you can see, the report of the coefficient is obviously negative, and the person is talking about increase, average increase, which is great. You have been able to detect this, but there is something else that needs also to be corrected in this statement. Which one?
Yeah, I think they haven't talked about the statistical significance of the results. So it is statistically significant.
Okay. With the 95 confidence interval. The confidence interval is good, is well reported. So it's year minus to minus. So yes, I think for the statistical significance, I can see that it's well reported, but I was hoping, so I mean, depending on your English level, and English is not my native language. So I was hoping also to see here, although is in good look and second look, I can see that, because in previous one, we were talking about 1 unit increase, isn't it? So, and the increase is a year. So perhaps the person should make it clear that, yeah, is every year, okay, every year is 1 year. Is that, I don't know, maybe it's my understanding of English, but I wanted to see that this should be clear that for the 1 unit increase, and this unit increase year, for us is obvious that is a year increase. But in any situation in the report, you should make sure that it's not every, 2 years or every year or something, that should be one year increase if the unit of measurement is 1 year. It's a year. I hope this is clear.
Yes, it is clear.
Yes, sir.
Okay, so you should not be talking about years, but we should talk about a specific measurement of that dependent variable. If it is year is 1 year, the unit is 1 year, and so on. And if it is every 2 years, every 5 years, this should be mentioned in the reporting. Good. Okay, so this is another reporting of result from another study. Age at interview. So given the above information, which is the correct combination of value for the model equation that we see there? So the model equation is alpha, the constant, plus beta times age. So you've got this table and you need to assess which one is the correct combination of values. So which one?
It's B, sir.
Is B.
B, yes,
What
sir.
is B? Okay. B is alpha is the constant. Yes, is here. And beta is the slope. Yes, correct. So this should be clear to you as expert. Which one is of the following is not true for linear regression in statistics? So A, it identified significant predictor for a continuous outcome variable. The B, it predicts an outcome of a binary variable with continuous variable. C, it quantifies a relationship between the two continuous variables. And D, it models a linear relationship between two continuous variables. Which one is not true?
B, sir. It's B.
That is,
It's B, sir.
yes, it's B, correct. Yeah.
Yeah.
So we are all together. Yes, B. Good. So this is one example of published study. So by the way, I'm also an editor of the journal. It's called the Journal of African Population Studies. So please, when you consider publishing next time, I'm now advertising this journal. So the Journal of African Population Studies is the journal of the Union of African Population Study. Is to do also with publication of health issue, population issues in Africa or African diaspora. So next time when you consider about publishing, please check this journal online, and perhaps also if anyone will want to be a reviewer, since now you are grounded into data science, so you'll be welcome to express such interest. in being as a reviewer or being part of the review board. So, and then
of the journal again.
Maybe let me, is this the Journal of African Population Studies? So perhaps I should put it in the chat, the link. So it's called Journal of African Population Studies. So you can just Google it. You will have the link there and see what is being published there. So now you have one example of a published study. So this is to do with serum leptin level in overweight children and adolescents. And this was published in the British Journal of Nutrition. So the report there, you can see highlighted here. So usually you have to report what was done in the simple regression or bivariate analysis and what was done in the multiple regression analysis. And we have seen in the previous slide that considering only age to predict the difference in blood pressure is not a good idea. And that is why we introduced the concept of multivariate analysis or multiple regression analysis. I guess you have noted the journal and that you are able to volunteer next time to be a reviewer or to submit your paper there and so on. So the next example I wanted to share in terms of reporting, good reporting. So this is one analysis that was reported in the British Journal of Nutrition. So you can see that, yeah, I was mentioning that you need to report what was done in the descriptive or bivariate analysis, but also more importantly, the complete story comes with the multivariate analysis. So we can see here that the author reporting that in the multivariate analysis with leptin as the dependent variable, which is clear, and the variable with significant association as independent variable, being female, greater BMI, reporting just the p-values, were determining factors in terms of the association between leptin and this variable. So the association with leptin and sex and between leptin and BMI, Z-score, they are shown in this table. So this is really very good reporting that you don't need to draw on, report all the tests and so on. And this is very important in terms of good reporting in published journal, because we are confronted by the space and confronted with the amount of text to be published in a paper. And also a combination of table and also graph is very, very important in terms of how to report regression analysis in a published paper. So this is a second example on the assessment of psychological distress among children and adolescents with food allergy. So you can see here, there were various multiple regression predicting child distress among children between the age of 8 and 17 years old. So, and here you can see also how the results are being reported. So there is the betas, that is the slope, and indicating whether this is statistically significant by a star or the level of significance in such a way that we are not putting a lot on the table, and the text being clear, so that the reviewers reviewing this paper is able to really quickly go through the text without any difficulties. So this is some sort of good reporting of what you have seen in terms of regression analysis and multiple regression analysis, and how now, as an expert, data science expert, you are able to report, you are able to assess, and you should be able in a position of giving your expert opinion on some of the reporting of this result. So I hope that this is clear. So now we can go through the summary. So I hope you understand the technique apart from the correlation. So you are able to understand the technique of how to analyze continuous dependent and independent variable, and that is the regression, linear regression analysis. So you are able to understand the concept of simple regression analysis, be able to, you can perform this in SPSS or Stata, and you are able to understand the equation that allow us to predict, interpret the result for simple regression analysis, and appreciate the need to check model assumption and whether the model assumption have been met or no. So this is really what I've been able to, to introduce to you since this morning. If there are questions or there are clarification to ask, please, the floor is yours now. Otherwise, there are some exercise that after this that you can just play yourself to see whether you can accomplish them by yourself with the concept that we have just seen today. So please let me know whether there is anything I've missed. So I can see one question here. Do we use regression in survival analysis? So this is a question. Do we use regression analysis in survival analysis? Yes. So survival analysis is a type of regression analysis. Survival analysis, remember when we talked about how to use regression, linear regression analysis. We started by saying that we have a quantitative dependent variable, and we also have a quantitative independent variable. then we can look for the association. And that was usually done by correlation, but we say, no, we can improve on correlation, then we can do it with simple linear regression analysis. And later, there was a question whether if we can only do this with quantitative independent variable, or we can also have a qualitative independent variable. And I did indicate that yes, we determine linearity, whether to use a linear regression analysis by the independent variable. So if the dependent variable is continuous, regardless of what is in the independent variable, we can use the linear regression analysis. So the dependent variable determines what type of regression we have. Then the question comes, when we have a qualitative outcome that is not quantitative, if we have a qualitative outcome, for example, a life or death, then we use the logistic regression analysis. So qualitative, so always with the dependent variable. Then survival analysis, what is it? Survival analysis, if your dependent variable is time to event data. Time to event data, time to getting COVID, for example. Time until you are dead, from birth to the time or the year or something. So that is time to event data. So that is your dependent variable. In that case, if you have such a dependent variable that is measured as time to event data, time until you get married, time until you divorce. So that is time to event data, time to event data. In that case, you can use the technique is called survival analysis, and it is a regression analysis. I hope that is clear. Is that clarifying the issue? The person that asked the question? Hello? So there is another question here. I'm not sure whether I've answered that question. Yeah, do we use regression in survival analysis? Yes, this is a survival analysis, is a type of regression analysis, but this time it's not, the dependent variable is not linear, it's a time to event data. So that is why it's called survival data. So survival regression analysis. So you can say in that way. Do we test for residual? Yes, you can test for residual, but this depends on the kind of technique. So if what we have discussed mostly here is to do with a linear regression model, testing linearity, testing normality, and so on. But in other technique, you may not test, you can test for residual, but you do not test them in the same way. What is the essence of testing for residual? So the essence of testing for residual is that the model you are having is a good one because you want to make prediction. And I gave the example of driving a car, testing for an engine oil and testing for something because you want to go from point A to point B, and you want to make sure that the car you will be driving in is a good one, and so that you may not run into problem when you are trying to go through this journey. So it's the same thing with regression. Is the model is a technique. So it's your car, and you want to check that what the prediction you have been making or you are going to make, because you are going to make this journey, and whether everything in that car is really perfect, is good. And do we report that in our research paper? Yes. When making the testing of residual, what I said is that mostly people assume that these steps are, they overlook them, and you just report your result without any mention of that. But as a good practice, and now as an expert, whether you are reviewing the paper or you are reporting your own result, you should at least mention whether the model fit was undertaken and whether you did check the model fit. It's really good practice to say that the model was, we fit this model, is a good model, or we did the sensitivity analysis of good model, and we are reporting the best performance model that we have. So this is something that you need. If you have not been doing this, you should do it now. About Bayesian method can be applied in regression analysis. Yes, Bayesian framework is a different way of looking at the same problem. So in the Bayesian framework, there also you have the dependent variable and also the independent variable. So there is nothing that differ from what we have been seeing today is to do what they call the conventional method. This is the traditional frequentist method. So that is to do with p-values. But the Bayesian analysis, as to contrast this with the frequentist analysis, what we have seen today, yes, this is a kind of technique, regression technique. You will need dependent variable y and independent variable x. So you can also have a simple and multiple regression, but this time in a Bayesian framework. So what is the difference? When the difference is that in the frequentist framework, the difference between y and x, as we can have, for example, the example of difference in blood pressure and the age of the patient, and you want to link the two together. So in the Bayesian framework, in this case, one of the difference will be that for age, you are able to have some prior knowledge of your participant or sample. So you may have some prior knowledge, for example, about the age distribution of your patient. This age distribution can be ranged from a certain range, and you can use that prior knowledge to increase the precision you are going to find between the blood pressure difference and the age. So there, you can use the prior knowledge to update your new information about the difference between blood pressure. So this is a completely different thinking, Bayesian framework, and they require a completely different class because there is complexity and it really differs dramatically from the frequencies, what we have just said here. And also there is one other difference in the fact that the independent variable age may be assumed to be fixed in the frequencies framework, but in the Bayesian framework, it is a random variable that has a distribution. So these are very serious stuff in terms of Bayesian analysis. I wish that data science, and I don't know why the organizer did not, we did not think about introducing even just some introductory concept into Bayesian analysis. I hope that maybe next time we should be able to do that because it's very important and is an emerging, most of the studies in public health, in public health now embrace the Bayesian thinking because not only frequentist approach, but also Bayesian analysis is in increase in terms of public health data analysis. So this is different, but the main concept of regression analysis can be done in frequentist approach and also in a Bayesian framework. So yeah, what is the difference between F squared and adjusted R squared and adjusted R squared? Yes, the adjustment is to do with, as we indicated, that sometimes you can have your variable. So it's dependent on the age, is dependent on the difference in blood pressure. But as we know that it's not only age that really matters in determining what goes on in the difference in blood pressure. So you can have like what you do about age, standardized mortality or mortality. So you adjust this or you standardize your R. So it's the same concept here with the R. So the observed one and the adjusted one, and you can adjust from other factors. Then when adding so many variables in modeling, multicollinearity problem can arise. So yes, and that is why, yes, we did not extend this today concept with multicollinearity. You are right. Yes, when you are having adding several variables, you should check whether these variables are not related. For example, you want to see the difference in blood pressure among your patient, and you want to predict this according to their age. But you believe that not only age is a factor, there is other factors, for example, the BMI of the patient. At the same time, there is also the weight of the person, and obesity usually is predicted by BMI or weight. So, and you can see that the two, if you add them in your model as independent variable, they can have computing impact on the difference in blood pressure. And that is why you have to make sure that the variable that you are including in the independent variable, they are not related. And that is the concept of multicollinearity. So that is why, how to check for this? you can have all your independent variable and just compute their correlation matrix. And when you compute the correlation matrix, you will see that, for example, the waste circumstances is very, very much related, has a high correlation between waste and BMI. So that is how you will know that there is multicollinarity. And now how to deal with that? Yes, there are technique. Then to detect is called the variance inflation factors. You are to see variance inflation factor is a measure of correlation between two variables. And then at the end, if the two, waste and BMI, is computing in the impact, the effect of the outcome, then you should decide to remove one. So in your independent variable, you should include only one variable. That may be, you may decide to go for BMI only or waste only, not both at the same time. And I hope these have answered all these questions, and there is no other question. Hello, are you still there?
Yes, Prof, you are here.
Yes.
Okay. Yeah, it's gone silent. I'm worried. So it's the question. Those was very good, very good question. But I hope that my clarification is clear.
You were clear, thank you.
Yeah. So if there is no further question, I think we should wrap up. And perhaps you will have some exercise that you can do at your own pleasure. And this is really just on trying yourself to familiarize with the concept of regression analysis. I know most of you have done it before, but the point here is not just doing it, but the point here is being in a position as data scientists to be able to authoritatively question the reporting, question the way the analysis has been conducted, and also for your own research, try to report correctly, and also try to argue correctly so that when you send a paper for publication, there are no major comments. There are no major comment made for your paper or waste of time for both the editor, the reviewers, and the audience, so that the reporting is done in a very concise and in a very clear manner. So this was really the point. So, and not that I know you have done this, but I hope by the end of this session, you are able to go authoritatively and conduct the business of regression. Although we have not seen all the form of regression analysis, we should be clear about this. So today's was only the very straightforward linear regression analysis. And we said you define your regression technique according to the dependent variable. you don't look at the independent variable. You look at the dependent variable. What is the nature of your dependent variable? If the nature of the dependent variable is a quantitative data, then you should proceed with the linear regression analysis, what we have done today. And this is mostly what people encounter, although there is also the logistic regression when your outcome is binary. And then I briefly touch on survival analysis, regression analysis. This is when your dependent variable is time to event data, that the time to death, time to having contracted the disease, or time to failure. Sometimes they refer it as failure data. If you hear about failure data, that is means survival data too. So with this, you will not use linear regression. You may not use the linear logistic regression. You have to use the survival regression analysis. And one of these survival analysis data is the data that take into account the time dimension of your outcome. Assuming that in your research, you are used to say that, for example, you are looking at mortality. Mortality, so you record mortality. You record mortality by saying that whether the person is dead or alive. But usually whether the person is dead or alive does not really mean anything. For me, the question of interest will be, since the person or what will, in terms of policy, what will be interesting to see is time, assuming that that person got sick, and what happened between contracting the disease and the time of death. So at that point, you can now decide with the survival. So the good technique is to consider those data, the regression, as not 0 and 1, the person is dead or alive, but just to see the time till that person was dead. And that is the survival analysis. So those are 3 major regression techniques that are being used in statistics. And of course, they are variant of that. So for now, I think that is what should be really noted. So if you don't have further question, I will try to close here. So I can see here when adding so many variables. Okay, this we have already answered. So I think there is in the chat, there is no other question. So Kelvin, so I think this should be, can we end up now? So bye everyone, and then see you next time.